बाद में आना अभी क्लास क्लास Hello, am I audible?
Yes, sir.
Okay, is my slide visible, right?
Yes, sir.
Is my slide visible to all of you?
Yes, sir.
Okay, so
Yes, sir.
let's start discussion for week 4. So myself, I am Paul, a PMRF research scholar from IIT Kharagpur, and I am assigned to be a PMRF TA for your course. My duties are I will be discussing some of the question that will be very much related to your assignment, so that when you will be doing your assignment, you will not feel it's totally new, right? So that is my goal. But before that, what I want to do is discuss some of the concepts that has been discussed in your week, so that you can have an idea, because I think this course is much more related to that numerical thing, right? Maths related approach, formulas and numerical things, but I will be focusing much on concepts, okay? And then we will be discussing some of the questions, right? So this course, introduction to machine learning, and it was taken by Professor Balraman Ravindran, professor and head of the department of data science and artificial intelligence, IIT Madras. Okay, so last week we have discussed regarding linear classification, logistic regression and LDA. Okay, now today we have two important topics to discuss. One is perceptron and another is support vector machine. Okay, so let's start our discussion with this perceptron. So perceptron, okay, I think someone is joining. Yeah, so let's start our discussion with perceptron. So perceptron, it is a linear supervised machine learning algorithm, and it is used for binary classification. Okay, now let's see how. First of all, for perceptron to apply, our data should be linearly separable. If our data is not linearly separable, then we cannot apply this machine learning algorithm called perceptron. Okay, so you can see these two graphs. Okay, so okay, guys. So you can see these two graphs, right? So okay. Yeah, you can see these two graphs, right? So the graph on the left side, you can see there are two type of classes. One denoted by this crosses and also orange color, and another class is denoted by triangle, and it is also separated by blue color. Okay, So these two classes can be linearly separable. Okay, so in this type of data we can apply this perceptron learning algorithm. But on the other hand, if we see this type of data, the data on the right side, here also you can see there are two type of classes, one denoted by cross and other denoted by triangle. But here you can see that this data is not linearly separable. So until the data is linearly separable, we cannot apply this perceptron learning algorithm. Okay, so the data on the left hand side we can be used for this perceptron learning algorithm, whereas data on the right hand side cannot be used for this perceptron learning algorithm. So first thing is regarding data set. Now what are the parameters and inputs in this perceptron learning algorithm? So again we have this inputs. Okay, inputs denoted by x1 x2, like here we have a two feature graph, like this one is x1 and this one is x2, means two feature group or two feature input data. That means there are two inputs, x1 and x2, right? So so if we talk about inputs in perceptron, we have x1 and x2, and apart from this we take one as a third input. Okay, and we keep this one as one in the first element of the matrix. Okay, we can form matrix, right? With our this inputs we can write it in a matrix form. Okay, so in this matrix form, this is a what type of matrix? This is a this is a column matrix, right? So here you can see here you can see we have two inputs, x1 as x2, and also we have added another input called 1. Okay, this input will take care of a extra coefficients that we will provide. So coefficients earlier also we have discussed, like earlier we have discussed with beta. Here we are using w. Okay, so w, there are three coefficients here: w1 for x1, w2 for x2, and w naught. For w naught, the input that we are using here is 1. Okay, so this is the concept. So two things are important: one is this this input, and second one is coefficients. Okay, this is you have seen earlier also. And another thing, there is a parameter here called learning rate. Okay, learning rate is related to search. Okay, means if the learning rate is less, that means we are doing learning rate is related to step size, you can say, or you can say the search size. Means if learning rate is small, okay, then you are searching the space much more time. Okay, if learning rate is large, then you are searching the space less time. So that is the concept of learning rate. Now how we can combine our inputs with coefficient? This is how we can combine our inputs with coefficient. We just do the dot product, that means w dot x, or you can say w dot x transpose. Okay, so w dot x transpose, when you will do this, this is your equation of that line separating the two data sets, that is w naught plus w1 x1 plus w2 x2. And now we have also studied the discriminant method method. That means discriminant method, what it tells is, if it is greater than 0, okay, if it is greater than 0, then we are telling our data form is in this region. If it is less than 0 or equal to 0, we are saying our data form is in this range. Okay, that is how we are separating here. Now the next thing, we have to update the weights. Okay, the weights we are choosing here, we are initializing randomly. Okay, but whenever we are randomly initializing our weight, this line this line which separates the two classes of dataset, it can take some misclassification error. Okay, so to avoid this, we have to update. So to avoid this, we have to update our data. We have to update our weights. Okay, so this is the concept of perceptron learning algorithm. Okay, so is this slide clear up to this? Any doubt? What type of data we can use perceptron learning algorithm? Okay, nice. Okay, okay, nice. So let's move on to the second thing, that is how to update the weights. So first, whatever weights are we are choosing, or whatever coefficients of the inputs we are choosing, we are randomly choosing. But whenever we are choosing it randomly, it happens is we can have misclassification error. That means if say the line is like this, but if I draw a line like this, like if I draw sorry, so if I draw a line like this, okay, so it can have misclassification error. It is separating the blue as well as this the triangles as well as crosses, but here this is a misclassification error. Okay, so that can happen when we are randomly choosing our coefficients or randomly choosing our weights. So our idea is to modify the weight so that it can we can remove this misclassification error. Okay, so how to update the weights? So first of all, here some randomly this is our data. Okay, and we have again two classes here it is denoted by triangle, and here it is denoted by crosses. Means there are two type of data sets. Okay, now we are randomly choosing the weights or coefficients. Okay, so we have chosen 0, 1 and zero point 0.5. Okay, and we have as we have two, yeah, as we have two inputs, so that is why this is our input matrix, that is 1 x1 and x2. Okay, so as we have 1 x1 and x2, that is why we have to select three coefficients. Okay, that is w1, w2 and w3. w1 will be corresponding to this 1 w naught, w1 and w2. w naught will be corresponding to this 1, and w1 will be corresponding to x1, w2 will be corresponding to x2. Now how we choose the equation of the line? We just multiply or dot product it. Okay, how we dot product it? W dot x or w dot xt, right? So w dot, whenever we will dot product it, our equation will be 0 dot 1, that is 0, 1 into x1, that is x1, and zero point 0.5 into x2 is 0.5 x 0.5 into x2 is 0.5 x2. Okay, so our equation will be x1 plus 0.5 x2 equals to 0. Okay, so now what we can do? We can multiply it by 2, that is 2x1 plus x2 equals to 0. So this is the equation of a straight line. We will make the straight line. Okay, so when we are making the straight line, as discussed earlier, as we have just randomly selected our weights, what happened here is we have a one misclassification, that misclassified data point. Okay, see the data point, if we see this line and choose it as the border, so you can see the left side of the border we can find triangles, the right side of the border we can find these crosses, but the right side we have one misclassified triangle. Okay, so that is the error. Now yeah, now this is the thing, this is from your classes. This is the thing. Now uh, what happens is we have two types of data point. Okay, the data point over here, that is crosses. Okay, so the crosses we are classified as y1. Okay, y equals to 1 and yi equals to 1. Okay, the triangles that we are classifying as yi equals to -1. Now if this is the equation that I have already told you, equation is w into beta naught plus wt into x, right? So if this is our equation, and yi equals to 1 is misclassified, like, yeah, let's say this is yi. Okay, and this is misclassified, yi equals to 1 is misclassified, then this is lesser than 0. Now there are two portion of this line, right? This portion and this portion. Okay, now if we see this portion, and if this is less than this is actually sorry, if we see this portion and classified it as it as and classified it as greater than 0. Okay, so this portion should be greater than 0 and this portion should be less than 0. Now if this is taking for misclassification. Okay, now what happens if this is misclassified? If this is misclassified, what happens is this should be here, but this we are writing here. So that is why for this point actually the equation should be, it should be less than 0, but now it is greater than 0, so that is what written here. Okay, similarly if a point is in that side, we can write this as this. Okay, and then these are the list of misclassified point. If we just sum up all the misclassified point, then this can be equation. Okay, yi into this is your equation of this line or any line that you can say, that is wt x plus beta naught, or you can simply say wt x. Okay, this is your thing. Now this thing separates the line, separates the portion of the space into two parts. One is less than 0 and one is greater than 0. The point in this side we are classifying it as I equals to 1, and point is this side we are classifying it as yi equals to minus 1. Now now let me erase this. Now this is according to your lectures, but how we are doing here, now we have to update the weights. This is our older weights, right? But we have to now update the weights. How the new updated weight can be found? The new updated weight can be found wi new equals to wi old plus eta del dxi. Now what is this d and y1 is same. Okay, if the point is in this side or the upper side, we will say it as 1, and if it is if it should be in the lower side, we will say as minus 1. Okay, now see about this point. Okay, this point should be at the lower side, but it is at the upper side. So if the point is at the lower side, so we will take d as minus 1 and we will update the weights. How we will update the weight? W naught or this W naught dash will be equal to W naught plus eta del x naught. Okay, eta is the learning rate, how much we want to search that space. Okay, now here the eta is taken 0.2. Okay, here the eta is taken 0.2 and d your point should be at the lower side. Okay, that is why it is taken as minus 1. So 0.2 into minus 1 into minus 1 because into 1, because our input for the W naught is 1. Similarly, our input for the W1 dash will be 2, right? And minus 1 because again this D should be minus 1 for all the cases, and also our learning rate will be same for all the cases, that is taken as 0.2 here. Okay, and W1 here is 1. Okay, so 1 plus 0.2 into minus 1 into 2, that will be 0.6. Similarly, we will find out W2 W2 plus eta dx2. W2 is 0.5. Okay, and eta 0.1, d is minus 1, and x2 is minus 2. Okay, x2 is the x2 is minus 2. Okay, so this is x2 okay, sorry, x2 is minus 2. Okay, let me see here. Okay,
So can you explain the weights updation again? Because the screen was stuck at that time.
okay, speed weight updation or coefficient updation. So the purpose of coefficient updation is if we have a misclassified point, right? If we have a misclassified point, then we have to shift the line either upwards or downwards, right? Here it can be seen well. Here see, we have randomly selected our weights. Okay, we have randomly selected our weights, and what we have done Yeah, we have randomly selected our weights over here, and what we have done, we have just done the this one wt into x. Okay, wt into x, that means
Yes.
our weights or coefficient into the inputs. Okay, 1 x1 and x2. Okay, now yeah, 1 x1 and x2. Now yeah, now how to update the weights, right? So how to update the weight? The weight will be updated by this formula. Okay, the new weight will be equal to old weight plus eta, that is the learning rate, into d is a parameter that is here, and xi is the coordinates of this point, the misclassified point. Okay, so up to this it is clear, right? Formula, is this clear?
Sir. Yes, sir.
Okay, now we will update the weights. Okay, now how this d is decided, that is the main question. Okay, we have wi as we have initial weight, so we have wi is w naught, w1, w2. So we have wi, right? We have this one. We have eta, yeah, we have eta it can be selected. So here in this question it is selected zero point 0.2. Okay, so eta is the learning rate. So eta is also we have xi. How xi we have? Xi will be dependent on coordinates of the misclassified point. Okay, so for this xi, you can see this point. This point is 2 comma minus 2, right? You can see here this point is 2 comma minus 2. Okay, so how our xi will be formed? Xi will be 1 because w naught will take 1 only, and x2 will, no, sorry, x1 will be 2. Okay, and
Sir,
x2,
exercise 1 because it is an upper bounder, sir. Here.
what can you please repeat?
For 2 comma minus 2 x, d would be 1, no, sir.
D would be 1. Now d should be d is minus 1. Why d is minus 1? Because this point should be in the lower bound, right? But it
Yeah.
is in the upper bound. That should is important, right? It should be in the lower bound. It is misclassified, but it should be in the
Okay.
lower bound. That is why minus 1. Okay, and
Yeah,
I
yeah.
was explaining about x1 will be 2 and x2 will be minus 2. Okay, because the coordinate of this point is 2 comma
Yeah.
minus 2. So we have w naught, w1, w2, we have etas, we have d, as this point should be in the lower half, that is why minus 1. So minus 1 and 1, and 1 2 and 1 2 and minus 2 1, because your w naught always take 1, and the coordinate of the point is 2 comma minus 2, that is why 2 minus 2. So by that we have updated our weights. And when we updated our weights, and when we have written the new equation, now you can check, or you can draw this line. Sorry, there should be some intercept, right? 2 by 9 should be some intercept. So now your, yeah, so yeah, now your new line will be formed. It will have an intercept 2 by 9. 2 by 9 will be somewhere here. So now new line will be formed like this. So it has clearly, when we have updated our weights, it has clearly taken this point at one side. Okay, so we have reduced the misclassified point from 1 to 0. Earlier there was one misclassified point, but when we have written this new equation, there is no misclassified point. Okay, so by that we have updated the weight. So is this thing clear about perceptron learning algorithm? Any doubt? Any doubt at any step? Okay. So important points to remember in perceptron learning algorithm. Again, I am saying first the data should be linearly separable. This is the most important point. Don't miss that. Second, the weight is randomly initialized. Okay, and then what the perceptron learning algorithm do is each by each step it updates the weight so that the misclassified points can be reduced. Okay, so that is how the perceptron learning algorithm works. Okay, so this is about perceptron learning algorithm. So now we will be moving our discussion to a new topic called support vector machines. Okay, now you can see this data set, right? This is a data set of a mass of a mouse. Okay, so now we have separated this data set into two classes. One, when the mass is less than something, we have said this is as non-obese, and if the mass is greater than some point, we have classified this as obese. Okay, so again I am repeating, this is a data set of a mouse. So we are telling that we have classified it into two class. One class, the mass is lesser than some threshold. We are talking it as we are telling it, or we are labeling it as non-obese. And when the mass is greater than some threshold, we are classifying it as obese. Okay, obese is given by this green color, non-obese given by red color. Okay, so this is all about our data set. Now how to separate our data, how to separate the two classes, that is our aim. So how to separate our two classes? We can have our threshold. So if I put a threshold here, somewhere here, I can probably separate our two data sets, two classes of data, two classes. Okay, so if I put here, so I can separate these two classes, that is non-obese and obese. Now a new data set, if it is it comes a new data set here. Okay, so if our new data set comes somewhere like here, so what we will term it as, we will term it as obese or non-obese.
Obese.
Obese, right? We will
Peace.
turn it as obese. But problem here is, the main problem here is, see, uh, this data set, this new data set is very close to our non-obese class. But still, as we have chosen our threshold somewhere like here, somewhere very close to non-obese. That is why this data set is close to non-obese. Still, we are classifying this as obese. Okay, so this is the problem. So how to deal with this kind of problem? How to deal with this kind of problem? Okay, this is okay. How to deal with this kind of problem? We can deal with this kind of problem by putting a threshold in between the two extreme points. Okay, now if we put our threshold exactly between the two extreme point, what will happen is, if here we will take one data set, then we can term it as non-obese. Earlier we are misclassifying it as obese, but now it can be classified as non-obese. Okay, so whenever we are putting this threshold exactly in between, putting this threshold or putting this classifier exactly in between extreme points of these two classes, then we call it as maximal margin classifier. Okay, and when we are talking about the maximum margin classifier, then there is again one term called margin. What is the margin? Margin is the distance between your threshold and your extreme point. Okay, so this margin will be shortest. Okay, when the threshold is at the midpoint. Now you will say, if the threshold is somewhere like here, then what will happen is, this margin will be smallest, but this margin will increase. Okay, so that is the problem. But the shortest distance can be achieved only when shortest distance from both the classifier can both the classes can be achieved when our threshold is exactly in between the two extreme points. Okay, and this type of classifier we call it maximal margin classifier. Why we call maximal margin classifier? Because we are maximizing the margin. Okay, earlier what happened is we have maximized at one side, but here the distance between the extreme point and the threshold was very small, so that is why it cannot be said as maximal margin classifier. But now, as we have chosen this threshold exactly in between exactly in between the two extremes, now we can clearly tell it as maximal margin classifier. Okay, so up to this it is clear, right? This is clear,
Sir,
right?
maximal margin classifier means the threshold lies between that uh, threshold value and extreme points, sir.
Maximal margin classifier means your margin should be maximum. How your margin should be can be maximum? Your margin can be maximum if your threshold is exactly in between the two extreme points of both the classes, right? Because if I shift the margin somewhere like here, so what will happen? At one side your margin will be small, but other side your margin will extend, right? So that is why it is not called as maximal margin classifier. But when it is called maximal margin classifier when your threshold is exactly in between the two threshold points. Okay, two extreme points.
Okay, sir.
Okay. Now let's move on to another case. Now up to here it is okay, but there is there is another problem here, is outliers. Okay, now now you see this curve. Okay, this curve or this data you see here. Okay, now here what is happening is this is your one class, this is your one class, this is your one class, but here there is an outlier that is very much here it is an outlier, right? But this outlier is is non-obese, but it is very much closer to this obese class, right? Now if we follow the same process over here, now here what will happen is we will like these are the two extreme points, right? Now whenever we will put our threshold exactly in between this two extreme point and we will have a new data point for a inference, what will happen is this will again not give you the right predicted class. Why this will not give you a right predicted class? Because now you will predict it as non-obese, but it is very much closer to this obese family, right? Obese family or obese class, right? So that is why again there is a problem. So our maximal margin classifier is super sensitive to this outliers. Okay, now to get rid of this, we are allowing misclassification in our margin. And whenever we are allowing misclassification in our margin, we call it as soft margin. Earlier, we are calling this as margin only. But whenever we are allowing this misclassification, we are calling it as soft margin. Okay, this point is misclassified. Okay, this point is misclassified or outlier, but still we are allowing room for this outlier. That is why this type of margin is known as soft margin. Okay, then earlier we are talking it as maximal margin classifier, but now this classifier will be called as soft margin classifier or our support vector classifier. Okay, and the name support vector classifier comes from the fact that the observation on the edges within the soft margin are called support vectors. So these two are our support vectors. Okay, the points at the extreme is known as our support vectors, or from wherever we are taking our soft margin, this points at the soft margin is known as our support vectors. Okay, so is it clear for the one dimensional data, this concept, how we reach there? Is this clear up to this? Hello, am I audible?
Yes, sir.
Okay, this is clear, right? Okay, let me assume this is clear to you all. Now we will extend that information that we have just discussed to two-dimensional input feature. Okay, earlier the input feature was one-dimensional, but now we are increasing our input feature to two-dimensional value. So whenever we are increasing our input feature to two-dimensional values, you can see over here. You can see over here, this is a two dimensional data, because we have two feature, right, x1 as well as x2. Okay, so you can say this is for mass, this is can be for age. Okay, so by that we are separating, we are extending our knowledge from one dimension to two dimension. Now here also we can definitely separate like this. We can definitely separate our classes of data. Here you can see this is the misclassified point. Okay, and this is a support vector, this is a support vector. So we can easily draw two line with the support vector and call it a soft margin. This blue color is your soft margin. Okay, and your threshold will be exactly in between your soft margin. So this red color is your threshold. So again we can separate our two classes with a line. Okay, earlier we are separating two classes with a point, because this is one dimensional data. So we are separating two points with the two classes with the points. Okay, this is not a line, this can be a point. Okay, this threshold is actually a point, right, point on this dimension. Okay, but here we have to separate our two classes of data with the help of line. Okay, so this is the difference between your one dimension and two dimension. Okay, now if we are extending from two dimension to three dimension, then we have to separate our data with the plane. Okay, and three dimension to four dimension, we have to separate our data with something called as hyperplane. Okay, this thing I have already discussed in the previous class also, but it's good to again talk this. So what is this hyperplane? Hyperplane is technically speaking, this one dimensional line can also be called as a hyperplane. Hyperplane are all flat affine subspaces are known as hyperplane. Okay, but we generally use the term hyperplane when we are talking about more than three features. Okay, that means four or more than four, then we are talking about hyperplane. So again I am repeating what I have told. If we have one dimensional data, okay, then we can separate it by a single point, that is zero dimension. One dimension data, then we can separate it by zero dimension. A point is a zero dimension. Okay, if we have two dimensional data like this, then we can separate the two classes by a line. Okay, this line is a one dimension. Now we have now you can say if we have three dimension data, then we can separate it by plane, and if we have four dimension data, then we can separate that by hyperplane. So this is the thing. Okay, so this is about support vectors. Now another thing that to discuss is the kernel concept. Now up to this the data can be linearly separated, but here is a data, like here you can say this data is about dosage. Okay, dosage, the dosage, how a person can be treated. If the dosage is accurately in this range only, the person can be treated. If the dosage is less than this range, the person is not cured. If the dosage is overdose, then also person will not get cured. Okay, so now how to solve this type of problem is our concern. Okay, so now how we will how we will deal with this kind of problem. We will deal this kind of problem by a thing called kernel. Okay, kernel. Okay, what is this kernel? The kernel, what it does is it increases our input feature into a higher dimension. Okay, like here there is a dimension for dosage only, right? Here is a one dimension data like x1, but what this kernel do is it will add another dimension to it. So how it will add another dimension to it? we are generally talking about a polynomial kernel. So what it will do, it will square the dosage in the y-axis. Means your x-axis will be dosage and y-axis will be dosage square. So whenever we are doing this, what will happen is, like this is 0.5, okay, this will be 0.25, this is this is say zero point 0.9, this will be 0.81, right? So like that your curve, your data points like this will be converted to this form. Okay, so whenever our data set is converted in this form, we can easily find the support vector. Okay, how we can find this? Here we cannot we cannot find a support vector. Here we cannot find a support vector because data is very much overlapping. Okay, and if we anywhere we will draw as a support vector, what will happen is we will have a lot of misclassified points. Okay, so rid of it, we are introducing this kernel concept. So what is this kernel concept? This kernel concept increases the dimensionality of your input feature. Okay, and it forms a new dimension. So whenever we are forming a new dimension, what will happen is this this data points now can be very well separated. Like now, how can this data point be separated? Now we can easily draw a line in between, like here. This is the your support vector. You can take two soft margin, like any point you can say, like this is your support vector, this is your support vector. So midpoint of this two support vector, you can midpoint of this two support vector will be your support vector classifier line. Okay, so this is the concept of kernel. So polynomial kernel, like this dosage square, polynomial kernel usually have a degree. Okay, so as we have to convert our 1D data into 2D data, so that is why we are using dosage square. If we have to convert 2D data into 3D data, then we will be using something like dosage cube. Okay, something like that. Okay, that is the thing. Now now okay, this is not important. This yeah, this is this figure is again related to your this support vector machines only. Here also one thing to notice, the support vector, okay, the equation of this support vector, that will be equal to 0. That means the point on this line will be equal to 0, but the point on this line will be equal to 1. Okay, the point on this line will be equal to -1. The point on this line will point ahead of this line will be greater than 1. The point below this line will be less than -1. Okay, that is related to your probability density function. Okay, px. So px related to px, but not exactly px. So that will be used in your questions. Okay, so this is the thing. So is this clear about this support vector, this kernel concept? Is it clear?
Sir, if we apply a kernel with any polynomial degree, then that p plus 1 degree is what we'll get, is it?
Can
For
you
the
please repeat?
Yeah, for that this thing, now you have applied on two-dimensional data, right? So if you have applied
This is a one dimensional feature data. Okay, now
okay,
what we have done is we have increased the one dimension into two dimension. So that is why we have used dosage to dosage square. Okay, this y axis line is dosage square, and when we have transform our data from dosage to dosage square, you can see here here if we are putting a support vector or a threshold anywhere in between, there is much more misclassification error, right? But when we have changed this dosage to dosage square and we have plotted our points, what happened is there is no misclassification error here, and we can very well separate this two group of data points. Okay.
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 So, but
In order to
sorry, so for that, which this should be a squared kernel, is it? For degree 2, we have to apply, is it?
Yeah.
Okay. But how do we calculate, like, how many, what is the degree of the kernel to be applied?
degree of the kernel that to be applied, like you have one dimensional data, that is why we have used 2 dimension, right? Like if you have 2 dimension data, you have to use a 3 dimension kernel. Okay, something like that.
Okay.
Which are the possible applications of this support vector machine?
Yeah, this is the application.
No, data point of view, this type of certain means.
So in which cases do we use perceptron learning and SVM, sir? Like, can
Perceptron
you?
learning can be only used when your data is linearly separable. Okay, here the data is not linearly separable, right? Still we have
Yeah.
used SVM, but perceptron can only be used when your data is linearly separable. Okay.
Sir.
Okay, so let's move on to the questions. Okay.
Also,
So
sir,
yeah, please.
can you explain me about soft margin and support vector? Like,
Yeah,
I'm a bit confused in that part.
yeah, exactly. Soft margin and support vector. Okay. Support vectors. Support vectors are the extreme point of your extreme point or extreme data points of your classes. Okay, you understood this margin? Okay, let me again explain. You understood this, right? We have
Yeah.
two groups. One is non-obese, denoted by our red point dots. We have obese, denoted by our green point dots. Okay, this is clear, right?
Yeah.
Okay, so our first step, how can we classify this two things, okay, separately. So
Yes.
how can we classify? By a threshold. So thing is where to put the threshold. So if I have put the threshold very close to one class like this, okay, what will happen is if we draw an inference point or draw a new testing data and found it over here, we will classify it as obese class. Why we will classify it as obese class? Because the
It
threshold
is now.
threshold is over here, right? That is why
Yes.
it is above the threshold value. That is why we will classify it as obese. Okay, but the problem here is we are seeing that this point is very close to this red group of points, right? That means non-obese,
So
but
this
we are.
green point could be misclassified here.
Yeah, can you please repeat?
So the green point would be misclassified near
Yeah.
the.
This green points is misclassified. Okay, so that is the thing. So to get rid of this, what we have done is we have done a next step. That is we have moved that this threshold exactly in between the two two extreme points. Okay, so when we are moving the threshold exactly in between the two threshold points, this type of classifier is known as maximal margin classifier. What is a margin? Margin is the distance between threshold and your extreme point. Okay, that is margin. Here we are maximizing the margin. Why we are calling it as maximizing the margin? See, what happens is, if like here what is happening is the margin between this extreme point and this threshold is very less, right? But
Yeah.
whenever we are putting it exactly in between the two extreme point, our margin will have maximum distance, right? That is why this type of classifier is known as maximal margin classifier. Up to this it is clear, right?
Yes, sir.
Okay, now next thing is what happens if we have a outlier data. Okay, like this set what is exactly happening is we have an outlier data here. The outlier, how we are telling it is it as a outlier data, because this data is very much far away from this group of points, but it is red. Okay, this is very much far away from this red point, but it is red, so that is why it is an outlier. Now what will happen in this type of cases is, see, whenever you are you will be taking threshold in between these 2 points, what will happen is what will happen, and when you will test it for a new classifier, new inference or new testing point, what will happen is this will be classified it as red point or non obese. Okay, but this point is close to this kind of points. So maximal margin outlier is maximum margin classifier is very much sensitive to outlier. To get rid of this, we have introduced soft margin. Earlier we are talking about margin. Margin is the distance between extreme point and threshold. But now we are introducing this soft margin. What this soft margin does is it takes care of this misclassified point. Okay, it does not consider this misclassified point. So our extreme point, it is considering this and this. Okay, extreme point, if it will consider it as it as like earlier, if it is consider it as extreme point and this is considered it as extreme point, the classifier is known as maximal margin classifier. But now we are omitting this outlier. Okay, so when we are omitting this outlier, so this type of margin formed is known as soft margin. Okay.
Yes,
Now
sir.
this type of whenever this type of margin is formed, and the threshold layer is known as support vector classifier, and the extreme points now without outlier is known as support vectors. Okay, this extreme points are known as support vector, and this threshold is known as support vector classifier, or support vector classifier, or soft margin classifier, or soft margin classifier, or support vector classifier. Okay.
Yes, sir.
Okay.
Sir, one doubt. In the lecture, he was mentioning that this kernel is something similar to applying basis expansion, right? Can you give some idea about this basis expansion, how we can think about it?
Basis expansion is like this only. Okay, the polynomial kernel that we are using, right? So that is the means basis expansion is like changing your data points to something else, like you have this data point 1 and 1 2 3, right? X1 x2 x3. Now you have a basis expansion like 1 x x square. Okay, 1 x1 x1 and x2 square. Now your data point will be like 1, because 1 is there. Now for x1 you will be changing to 4, and for x2 you will be changing to x2 square, so that is why we will be changing to 9. So this same thing. Okay, kernel, that is some concept of this basis expansion. Okay.
Okay, thank you.
Now we will be quickly coming into our questions that are very similar to your assignment question. This is not your assignment question. Assignment you have to do it yourself because it is graded, but I will be discussing similar question like your assignment, so you will get some of the concepts. Okay, so this is the first question for a 2 class classification problem. We use an SVM classifier and obtain the following separating hyperplane. We have marked 4 instances or 4 data points, okay, of the training data. Identify the point which will have the most impact on the shape of the boundary on its removal. 1, 2, 3 or 4. So any guesses for this? Okay, 1. Anyone else? Yeah, 1. Okay, yeah, you are absolutely right. Your answer will be A or 1. Why? Because this is a support vector. How it is a support vector? Because this is the extreme point closest to your classifier. That is why this is a support vector. Okay, this is a support vector, and for this class you can say this is a support vector. Okay, this let me call it as 1 star. Okay, this 1 and 1 star, these 2 points are the support vector. So these points will have maximum impact on your boundary line. The other points, as they are not the support vector, so they will not have influence on your data points. Okay, so option A will be your answer. Okay, is this clear, right? Okay, I think it is clear. Now let me move to the next question. SVM cannot classify data that is not linearly separable even if we transform it to a higher dimension. True, false cannot be said. Okay, false, right? Anyone else? Okay, yeah, absolutely right. We have just seen with the help of kernels, we can, yeah, Sandeep is also right. Yeah, we have just seen with the help of this kernels, even if the data is not linearly separable, when we are using the kernels and move it to a higher dimension, we can easily separate our data points. So that is how SVM works. Okay, so that is why this statement is false. Okay, so SVM can classify data that is not linearly separable if it is transformed to a higher dimensional space with the help of kernels. Okay, so option B is right. Okay, so any doubt in this? Okay, so let me move on to the next question. Consider a soft margin SVM with a linear kernel and no slack variables trained on endpoints. The number of support vectors returned is k. Okay, by adding one extra point to the data set and retaining the classifier, what is the maximum possible number of support vectors that can be returned? Okay, tuning parameter c. Okay, so any guesses? Yeah, d k plus 1. Okay, 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 d. Yeah, it can be D or it can be C. Okay, the maximum number of support vector that can be returned is equal to number of training points. Okay, so this k is actually equal to n here, because the maximum number of this support vector, okay, here it is not written the maximum number of support vector, but your maximum number of support vector is always equal to your data points. Now we are increasing data points, that is why your maximum number of support vector will be equal to n plus 1, that is C is your right answer. Okay, because here the it is not mentioned maximum number of support vector, right? But your maximum number of support vector will always be equal to your number of data points. That is why when we are increasing the data points, it will be equal to n plus 1. So option C is your correct answer. Okay, okay, so let me move to the next question. Consider the data set given below. Claim the PLA or Perceptron learning algorithm can learn a classifier that achieves zero misclassification error on the training data. This claim is A true, B false, C depends on initial weights, D true only if we normalize feature vector before applying PLA. So, any guesses for this? Okay, someone is telling true. Okay, so we have to see if our data, okay, this is our data, okay, this is our x1, this is our x2, and this is our class, okay, or you can tell yi or y1 yi, okay. So this is the thing, x1, x2, and yi. Now we will be forming our two-dimension input space. Okay, so 0 0 will give a. Let's say that a, let's denote a with circle, and let's denote b with star. Okay, so 0 0 0 0 will be this point. Okay, this is okay, let me mark, this is 0, this is 1, this is 1, right? So 0 0 0 0 is this point, right? And it will be class A, that means let's mark it as this. Now 0 1 0 1 will be B, so 0 1 0 1 will be B, so let's mark it as cross. 1 0 1 0 will be B, so let's mark it as this. And 1 1 1 1 will be your A means let's this. So can this be linearly separable? Because remember, always PLA works when your data is linearly separable. So can this be linearly separable? We have two crosses here and two crosses here. So is this linearly separable? And
False.
answer is no. This is not linearly separable. That is why this claim is false. Okay, this PLA cannot be applied. Now I have told you about PLA. PLA does not depends on the initial weights. It does not depend on the initial weights. Okay, because it will keep on modifying the weight until it get rid of that misclassified point. Okay, so that is why this is false, right? And this is also false. True only if we normalize the feature vector before applying PLA. Now if you can normalize also, then also if you will normalize PLA means we are reducing the dimension, but even if you will normalize it, we cannot separate. Okay, because remember, if we can move from lower dimension to higher dimension only, then only we can get rid of this linearity problem, right? As we have seen in SVM. But here they are applying PLA. PLA reduces the feature. So if you are reducing features, so there is no chance of separating the two classes with a linear classifier. Okay, so this is also false. So option B is your right answer. Okay.
So what do you mean by normalize? We have to divide by normal. No?
Only if we normalize. No, PLA actually we are the things which are correlated. Okay, we are transforming it to a new feature. Okay, so that is the thing. That means we are reducing features here. So whenever we are reducing feature, we cannot get rid of this linearity problem. If we can increase feature, then only there can be a chance that we can get rid of this linearity problem. So this is the thing. Okay.
Okay.
Okay. So now move on to the. Okay, is this clear? This is a good question. Is this clear? This covers much of your PLA thing. So is this clear? Any doubt regarding this? Any doubt in this graph? How I have told this is not linearly separable? Any doubt? Yeah, clear. Nice. So let's move on to the next question. Which of the following is true about perceptron classifier? It can learn a OR function. Okay, OR and NOT, XOR, these are gates. Okay, Boolean gates. Okay, so here it has been asked, it can learn an OR function, it can learn an AND function. The obtained separating hyperplane depends on the order in which the points are presented in the training process. Okay, for a linearly separable problem, there exists some initialization of weight which might lead to a non-convergent case. So any guesses for this?
Sir, ABC.
ABC, ABC, okay. Not D, right? Yeah, not D. So yeah, you are right, not D. So this is false, right? Now how A, B and C are correct? Again we have to make this curves, okay? Now we are talking about OR function, okay? This is for OR, okay? OR is your output will only be one, only both the inputs are true, or your output will be or is your output will be true whenever each of one of your output is true. That means this is false and false, so false. But here false and true, so true. Now true and false, again true, 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 true. So this is your OR curve. So whenever we are okay, let's for 0 we will tell it at dot, and for 1 we will tell it at cross. Okay, so 0 0 0, that means this. Okay, this is 1, this is 1. Okay, so better okay, 0 0 0. Now 0 1, that is 1, that means 0 1 is this, so 1, that means this. 1 0 is 1, that means again this, and 1 1 is 1, that means again this. Okay, so now it can be separated, right? Here we can draw a plane or line as we are talking about 2 dimensions, so line. So here we can draw infinite number of lines and we can separate the two classes. So it can learn an OR function, that is true. Now what about our this AND function? What is AND? AND is uh, it will be true only when both your inputs are true. That means 0 0 it will false, 0 1 also it will be false, 1 0 is false, and 1 1 only it will be true. So let's erase it and let's make a new one. Okay, let's make a new curve, and what 0 0. Okay, 0 0 is 0. Okay, 0 we are using dots. Okay, so 0 0 0, 0 1 0 1 is 0, again is 0. Now 1 0 1 0 is 1 0, again this is 0, 1 0 means here again is 0, 1 1 only it will be 1. So again we can separate this curve. How we can separate? Like here if we draw a line here, an infinite number of line, we can easily separate our crosses as well as dots. Okay, so that is why, that means we can easily separate our two type of classes. That is why again a perceptron can learn AND function. Now the obtained separating hyperplane depends on the order in which the points are presented in the training space. Okay, so yeah, it depends on the order, because your perceptron learning algorithm always depends on your input. Okay, so if your x1 and x2 is interchanged, like x1 is 1 and x2 is like 0, and we are interchanging it 1 0 to 0 1, then definitely there will be changes in our results. So C is also true. D is not true, because I have already told you it can take any of the the perceptron. If it is linearly separable, then choosing any type of any weights, it will converge and it will get rid of the misclassified points. So A, B, C is your correct answer. Okay, so this is the thing. So let's move on to the next thing. Let xi be the input instance with label yi. If yi, this is the that wt. Okay, this is nothing but that wtx. Okay, this is wtx, beta naught plus wtx, you can tell. So yi dot this equation is greater than 1. So xi is not a support vector, xi is a support vector, xi is either outlier or support vector, xi may or may not be a support vector depending on other points. So any guesses for this? Okay, someone is telling not a support vector. Okay, yeah, someone is telling A. Okay, any other guesses? Yeah. So yeah, this is correct. Your option A is the correct answer. You can see, you can clearly visualize by this. I have already told you that yi into this will be equal to 1 when your data point will be at this line. That means if your data point in this line, that is a support vector. So yi will be equal to 1 when your data point will be at this line. The yi will be less than yi will be this equation will be equal to 0 when your data point is at this line, black line. This equation will be equal to -1 when your data point is at this line. Okay, because we have two classes, one we are denoting by +1 and one we are denoting by -1. That is why the point on this line will the equation for points on this line will be equal to -1. The equation above the points on this line will be greater than 1. Similarly, the equation similarly value for data points that is beyond this line will be lesser than -1. So this is the calculation. Now it is told that it is greater than 1. As it is greater than 1, so these are all the points, not this point. Okay, let me erase it and again make it. Okay, so this is talking about this point. Whenever we are talking about all these points, so our equation will be greater than 1. Okay, so we know that support vector will be equal to 1 and not greater than 1. If it is greater than 1, then your points are not a support vector. So option A. So option A is your correct answer. Okay. So any doubt regarding this? Again I am repeating this, when your data point is in this line, this is a support vector, right? And your equation will be equal to 1. When your data points will be in this line, your equation will be -1. When it is beyond this, then beyond this on the right hand side, that means all this point, then your equation will be greater than 1, and these points are not support vector. If it is less than -1 also, your equation will be less than -1, and these points are again not support vectors. Okay, so this is the thing. So option A is your correct answer. Okay, so let me move on to the next question. Suppose we are using a linear kernel SVM to build a classifier for a two class problem where training data points are linearly separable. In general, will the classifier trained in this manner will always be same as classifier trained using Perceptron algorithm on the same training data? So yes or no, or C cannot be said. Any guesses? Okay, someone is telling A. Okay, so option B is correct. Okay, because whenever we are talking about hyperplane, so hyperplane will take the maximal margin approach. Okay, but your perceptron does not take the maximal margin approach. Okay, this is the difference between these two type of things. Okay, so maximal margin approach means it will ensure that your support vectors are as far as part, but in perceptron learning algorithm, it will not ensure that. It will just make a line, and that will be your classifier. So this is the difference. That is why option B is your right option. Okay, the hyperplane written by SVM approach will have a maximal margin, whereas no such guarantee can be given for a hyperplane identified using perceptron algorithm. So option B is your correct answer. Okay, any doubt regarding this? Okay, so question number 8, suppose you have trained an SVM which is not performing well, and hence you have constructed more features from existing features for the model. Which of the following statements may be true? We are lowering the bias, we are lowering the variance, we are increasing the bias, we are increasing the variance. So which option will be right? Yeah, someone is telling we are lowering the variance. We are lowering the variance. Okay. So no, your answer is not correct. I have already discussed this bias variance trade-off in the first class. So what happens is, whenever we are increasing the feature, we are making the model more complex, and whenever the model becomes more complex, it is lowering the bias but increasing the variance. Okay, so option A is correct, that is we are lowering the bias and we are increasing the variance. So again I am repeating, whenever we are making a more complex model, or whenever the features or anything we are just complicating our model, what will happen is our bias will be lower. Okay, and our variance will increase. So option A as well as option D is correct. Okay, okay, lowering the bias and increasing the variance. No, reverse of this. Okay, lowering the bias, increasing the variance. Okay, okay, which of the following is are true regarding an SVM? For two-dimensional data points, the separating hyperplane learned by a linear SVM will be a straight line. Option B, in theory, a Gaussian kernel SVM can model any complex separating hyperplane. Option C, overfitting in an SVM is a function of number of support vectors. Okay, option D, if number of features increases, model will less overfit. Okay, so any guesses for this?
Sir, AB.
AB, okay, AB, not C, overfitting in an SVM function of number
Yes,
of,
sir. I think ABC.
yeah, so A, B and C is the right answer. Okay, for two-dimensional data point, the separating hyperplane learned by a linear SVM will be a straight line. As I have already said, your dimension of the SVM will be n minus p minus 1. Okay, if p is your number of features, like you have two feature input x1 and x2, then you have to separate it by a line. A line is a one dimension hyperplane. Okay, so that is the concept. So that is why linear hyperplane. If we have one dimensional data, then p minus 1 is 0. That means we have to separate our two classes of data with the point. So option A is correct. Okay, because we have two dimensional data, so we will be separating it by one dimensional thing, that is straight line. Okay, so option A is correct. Theory of Gaussian kernel SVM can model any complex separating hyperplane. So again, this is a theoretical thing. So what like we have discussed about polynomial kernel, if we are changing if we are dealing with Gaussian kernel SVM, so it can model any complex hyperplane. Okay, C is overfitting in an SVM is a function of number of support vectors. So if we have more number of support vectors, so we are literally overfitting our data. Overfitting is not recommended at all in machine learning. What is overfitting? Overfitting means that data is very much prone to its training set. So what happens is, whenever we are testing it to whenever we are inferencing it to a test set, the model will not perform at all. Okay, so option C is also correct. So option D, number of feature increases, model will less overfit. So if number of feature increases, again we are complicating the model. So your model will actually more overfit, not less overfit. So option A, B as well as C is the right option. So for a two-dimensional data, that for a two-dimensional data, 2 minus 1, that means one dimension hyperplane, that means we are having a straight line. So in theory, we can do with the help of kernel function, we are increasing the input feature such that we can have a hyperplane separating this complex data. Now overfitting in an SVM is a function of number of support vectors. So A, B as well as C is correct. Okay. Now moving on to the next question. Consider a Boolean function in three variable. It returns true if two or okay. It returns true if two or more variables are true. False otherwise. Can this function be implemented with the Perceptron algorithm? So again we have to see if our model is linear or not. Okay, that we have to see. So we have three data features here: x1, x2 and x3, and we have been told that it returns true if two or more variables are true. Okay, so true, that means true. Okay, true, that means true. True, false, again true. True, false, true, we have two trues, that is why true. True, false, this will be false. False, true, again we will have true. False, true, false, we will have false here, because we have two false. False, true, again false, and three false, then false. Okay, so if we are denoting our true by a green point, and if we are denoting our false by a red point, we can make this graph in anything, any Excel or anything, and we can clearly see if we can separate this two group by a plane or not, because it is a three-dimensional data, so we have to separate it by a plane. So we have to see this. Okay, now here you can see true can be considered as 1. Okay, so 1 1 0, sorry, 1 1 1 1 1 1. So 1 1 1, the answer is 1, that means green point. Okay, green. True means green, and false means red. Okay, false means red or 0. Okay, so 1 1 1, here you can see 1 1 1, so 1 1 1, so we are talking about this point. Okay, so this point is denoted by green because it is true. Okay, now 1 1 1 0, 1 1 0, 1 x1 is 1, x2 is again 1, okay, 1 1 and 0. So this point we are talking about 1 1 0. So again 1 1 0, the y value is true, that is why it is a green point. Similarly we will be testing on all the points and see this. Now is this can be separated by a plane? If yes, then our perceptron algorithm can be applied. If no, our perceptron learning algorithm cannot be applied. So according to me, this cannot be separated by a plane, because if you will have a plane, okay, okay. Actually, this point is 1 1 1. Okay, this point is 1 1 1. So we have this point, this point, this point, and this point. Okay, so this cannot be separated by any plane according to me. If it can be separated, then we will say perceptron learning algorithm can be implemented. But if it we cannot separate this by any plane, so perceptron learning algorithm cannot be implemented. So according to me, the option B is right. Okay, so you got it, how to solve this type of question?
Sir, but if we connect that 111 and those other 2 points, what is that?
1 1 1, this point, and
Those, if you connect it with a triangle, then you can, the other point is all anyway with on the other side of the triangle, right?
triangle. But how you will separate this point and this point? Actually a plane can be drawn here, but this point and this point is intersecting. If you draw a plane over here, right, if you can separate, then it is okay. But according to me, cannot be separated, because this point and this point will come in. So if you will draw a plane over here like this, okay, then this point and this point is intersecting. So that is why according to me it cannot. If you can, then definitely it can be done, but according to me you cannot. So that is why option B is right.
Okay.
Okay, so that's all for today. Any particular doubt in any part, whatever I have discussed?
So once can you explain fifth, sixth, and seventh question?
Fifth, sixth, and seventh.
Yes.
Okay. Okay. Fifth question, it is an important question. Which of the following is true about the perceptron classifier? I have already told you perceptron classifier can only be applied when we have a data points can be separated by a linear thing. Okay, or data point is if data point is linearly separable, then only we can apply this perceptron algorithm. So this two option we have been told to test it with or and function. Okay, so this is the hello,
Yeah.
yeah, or an and function, right? So here you can see this is the
I understood this part. Why D is not correct in this question?
okay,
Option D.
okay, 1 minute. Okay, so for a linearly separable problem, there exists some initialization of weight which might lead to non-convergent cases. Okay, so there is no weight that can lead to non-convergent cases. Whatever weight we have, our perceptron learning algorithm will modify the weight again and again, so that there will be no misclassified point. Okay, that is how the perceptron learning algorithm works. That is why D is incorrect.
Yes, sir. And
Okay.
why is C correct? Like
The
I'm confused with this
in
question.
which the obtained separating hyperplane depends on the order in which points are presented. Yeah, order is important, right? Because order is very important, because if you see this, like whenever we are doing this weight updation, if you see this, the if the order of the point, like uh, like if the order of the point, if the coordinate of the point here also changes due to the order of the point. Okay, so here what will happen is our x1 and x2 of this point will change. So according to me, that is why the order of the point will have influence on your influence on your this perceptron learning algorithm. Okay.
Yes.
Okay. Now sixth, yeah. Sixth is again an important question. Sixth, see yi is the class value. Okay, yi will be 1 for this green color, yi will be minus 1 for this blue color point. Okay, now we are separating it by a optimal hyperplane. So whenever we are separating it with the optimal hyperplane, we have two soft margin. Okay, one soft margin with one support vector, another soft margin with another support vector. Okay, now there is an equation given here. This equation will be for this line. Okay, and this will be equal to 0 when your data point will be on this line. Okay, this will be equal to 0 when your data point will be on this line. Now
Yes.
if your data point will be on this line, what will happen is this thing will be equal to minus of 1. Okay, and whenever your data point will be on this line, this thing will be equal to plus of 1. And here it was telling when a condition when it is greater than 1. So whenever it is greater than 1, then it is discussing about this very points and not the support vector, because if it is equal to 1, then it is discussing about this support vector. But as it is greater than 1, then this it is discussing about all the these points that are not support vector. So option A is your correct answer. Okay.
So if it is less than 1, it would not be a support vector, or no, sir.
Less
In this,
than 1, yeah, again less than 1, yeah, less than 1, less than 1, no, less than 1, again it will not a support vector, because less than 1 there is no points less than 1. Okay, less than 1 means how much less than 1? Less than 1, if it is minus 1, then it can be support vector.
yes,
Okay,
sir.
and less than minus 1, then again it is not support vector.
Hmm.
Now question number 7, suppose we are using a linear kernel SVM to build classifier for two class problem where the training data points are linearly separable. In general, will the classifier trained in this manner will always be seen as classifier trained using Perceptron learning algorithm. So both this algorithm we have applied a different approach. For perceptron learning algorithm, what we are doing, we are initializing some weight and then we are updating the weight so that we can vary the slope of the line and we can get rid of the misclassified point. But in case of support vector machine, we are talking about maximizing the margin of the support vectors. Okay, so we are talking about maximal margin approach. So that is why SVM and perceptron learning algorithm are not same. So option B is right. Okay.
Yes.
Okay. So any doubt regarding any other question? Okay. So by this I am terminating the session for today. We will meet on the next Monday. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.